Good morning, everyone. We'll be starting in 1 to 2 minutes time. Alright, good morning again, everyone. And today's session is going to be focused on doing some practice problems. In particular, what sort of problems you may be expecting to come on the midterm next week, Wednesday, as well as some additional problems that were requested from the polls online on Mind Learning. And if we do have any additional time once we finish these problems, if there are any other general problems in particular or any questions that we can address in the 2-hour time frame, we can go about addressing it until we close off the session in particular. So the last time when I was doing problem set 2A, I was able to complete question 7, but I did went over time in particular. So this question basically was completed, showing how to go about doing the FFT fit and identify the frequency components and so forth and whatnot. The other two questions that were requested to do were question 8 and question 9, and I believe in Monday's session I did the deconvolution process, which was question 11. So we'll start with question 8 and then do question 9 here for this problem set, and then for problem set 2B, we got requests for question 2, question 3, and question 4. Question 2 is basically just a MATLAB code sketch, which I can give you guys at any point of time, so we'll bypass question 2 for the time being, but then we'll focus on question 3 and question 4 in particular. The reason for this being is that question 3 is like a type of question you may get on your final exams, whereas question 4 could be a possible question that you could get on your midterm in particular. So let's start with question 8 from problem set 2A, and while I'm doing these questions, make sure that you do ask any relevant questions, in particular if you don't understand any particular steps and so forth, so I can address them immediately and we can get prompt feedback regarding this. Okay, so question 8A basically says that the FFT butterfly diagram shown in figure question 8 represents the final processing stage for an 8-point FFT. We just need to complete this FFT stage. Yeah, I know here it says Q7, this actually is supposed to be Q8, so put a comment here on this. This will be Q8. Nice, I'll know to fix that. Alright. So all we just need to do here is just to complete this butterfly diagram, and then the next part of the question asks, knowing that we know what's the sampling frequency, being 1200 Hz, what's going to be the amplitude and frequencies of the two largest spectral components present in the signal. And we'll tackle that right after once we complete this butterfly diagram in particular. So let me bring up my whiteboard here. And let's start doing this butterfly diagram in particular. So here was 9 minus 4 minus 3j, 3 minus 4 plus j, 6, 2 minus 4j, minus 2, and 2 plus 4j. And then let's just backtrack here a little bit. Right, we had boxes here to represent what we needed, and then the output stage. Right. So this being the final output stage of an 8-point FFT is such that because it's the final stage, that's going to be 2 to the 3 here. And it's the third decimation stage. And because it's 2 to the 3, that means 2 to the 3 is 8. And we need to group half of that in particular. So the first half of these 8 values will have no total factors or -1s associated with them. But the second half of these 8 values will have total factors and -1s associated with them. And because it's 2 to 3, that means the total factors being wk of n, or we can say wn of k, n here will go up to 8. So that means the total factors associated with these 4 values here, meaning the second half of the 8 values, are going to be W80 to W83, and then having the -1s to represent the other half of the total factors in particular. So this here will go W80, one will be W81, will be W82, there will be W83. And then we need to have the associated -1s because of the symmetric property of the total factors. I have a -1 here, next -1 here, and so forth. And then we can actually draw our butterfly diagram associated. So the first value here that doesn't have a total factor will match to the first value here that does have a total factor and -1 in drawing the butterfly matching for this. So we can just draw this arrow here, we can draw this one going across as well. And then we know that in between the total factor and -1 there needs to be a cross point. So that cross point will go here. And then the next cross point will go here as well to complete the butterfly for these 2 values in particular. Now, in doing the calculations for these, this here is going to be 9 going straight across, and then there's a 6, W8 of 0, W8 of 0. If you remember, the equation for the total factor is e to the minus j 2 pi k on n, and k here will be going from 0 to 7. So W8 of 0 is just going to be a value of 1, so that's 9, add 6 by 1, so that means we'll get a value here of 15. And then similarly, because we have to also calculate for the next half of the butterfly here, this is 9, add 6 by 1 here, my -1, so this is going to be 9 minus 6, so this value here will just work out to be 3. And then we just repeat the process as we keep on going down in the butterfly. So for the second value that doesn't have a total factor, when we're matching this to the second value that does have a total factor, so we just draw arrows across here. And we know there's a cross point in between the total factor and -1. And to draw the next half of the butterfly, there needs to be another cross point as well. And then we can go about doing the calculations for this in particular. So this calculation here, I'm going to write it out for you, is going to be, let's say we're solving for this part here in particular. This here is going to be -4 minus 3j, add 2 minus 4j by W8 of 1. And we know that Wn of k here is equal to e to the minus j 2 pi k n, which is basically, if we're trying to solve for W8 of 1, this will be e to the minus j 2 pi by 1 divided by 8. And we can just plug this in straight into any complex calculator or MATLAB or Octave. So I'm just pulling up Octave here to show you guys how I'll go about doing the calculations. Bring Octave up here. Shift this down a little bit. So we can say W here is equal to the exponent of minus j by 2 pi by 1 divided by 8. And we get our total factor here. So that here is going to be 0.7071. Let's bring that back up. Check that what that was. Minus the same thing with j. And then we just calculate that out accordingly for the entire thing. So down here, bring that up Octave here. Let's just zoom this a little bit. That way you guys can actually see this. So then we can just type in our equation here, being minus 4 minus 3 by j. Add W by 2 minus 4 by j. And you can see here that we get our calculation giving us the correct value for the output of the thing, of the butterfly diagram. I'm just going to check my answers here to make sure that was correct. Yes, that was correct too. Alright, so because we just round out our answers to 3 decimal places, we'll just round up or down accordingly because of the 4th decimal place given the calculations. So for this particular one, because we did the calculation here, this one will go just resolve to minus 5.414 minus 7.243. And then similarly, because we're doing the other half of this butterfly here, that means the equation here, when you're trying to calculate for the next half here, it just means you're going to have a minus 1 factored in for the calculation. So you can just go back here into Octave and you can just go up 1 to pull back up the calculations and just multiply by minus 1 here, and you can get the other half of the butterfly here calculated out for you immediately during this calculation. So in this case, our answer here is given for the second half. I'm just going to round that up to 3 decimal places. So this here is going to be minus 2.586 plus 1.243. So we can just keep on repeating that process as we keep on going to calculate for all the total factors and all our output stages of the butterfly diagram accordingly. Let's say if you did wish to calculate out for all the total factors in one go. So that means we'd have to define what n is. So we can say n here is equal to 8. And then k, because k goes 0 to n minus 1, is going to be 0 to 7. So we got a vector here for k going 0 to 7 in increments of 1. And then we can say w here is equal to the exponent of minus j by 2 by pi by k divided by n. And then we have an entire w vector here giving us all the total factors associated for w of 8 in this particular case. And remember, MATLAB and Octave, the indexes for any vector or any matrix here does not start at 0, it starts at 1. So like if we put W of 0 here, it's going to complain and be like, it doesn't know what that subscript is. So you'll have W of 1 here being, or W8 of 0, and so forth and whatnot. So this is if you want to calculate all the total factors in one go. If you don't want to, you can just do the process from before, where we just calculate out each total factor in turn, which we did here, each calculation. But it depends on your style, on how you want to go about doing the calculations and so forth, regardless. One thing to note though is that once you're doing any of these FFT questions, the total factors themselves do carry marks. So make sure that you do calculate out the total factors and you write them out on your scripts, because each one of those total factors do carry marks for those butterfly diagrams and those FFT calculations. And that's why it's important to show all working, in particular, like what I just did here. When I wrote out the stages here in particular, you need to actually show all of these working in particular for each one of the calculations and so forth and whatnot. You don't need to like go into extreme detail, showing like, okay, what W8 is, substitute that in, and then do the multiplications by hand. You can just write out the equation as is, and then just use MATLAB or Octave to do the calculation for you and just write out the result. But we still need to see this working here in particular to verify that you're on the right track. It also helps that, let's say if you did happen to write a wrong answer as a result of you just happen to write something wrong when you're transcribing it from MATLAB or Octave, but the calculation was correct, we can still award you some marks regardless, because we can see, okay, you were on the right track, instead of just writing the answer and then we have no proof indicating how you went about getting the answer. So that's why it's important to show all working, and that's going to be a major instruction on the front page of your midterms and your final exams. Make sure that you do show all working, because it does help us to give you additional marks in case if you do happen to write the wrong answer. Yes, you're free to use MATLAB or Octave for the midterm as you see fit. Just make sure that you do write out the equations for the calculations, and then you can just use MATLAB or Octave like if it's just a calculator to just calculate out the final result for you. You can also use it to verify your answers as well, because there's a handy FFT function inside there that can give you the final answer immediately, and you can use that as verification to know if you are approaching towards the correct final answer. Alright, so let's just complete this butterfly diagram here in particular. So we're going to do this for the third value that doesn't have a total factor. Compare it with the third value that does have a total factor. And we just draw cross points accordingly as well. And in the interest of time, I'm just going to put down what the answer is here. So this one should be 3 plus j, and this one here is going to be 3 minus 2j. And then we're just going to complete here. It should be minus 2586 minus 1.243j. This one should be minus 5.414 plus 7.243j. So that will just give us towards the end of our question 8 here, which is basically to calculate out the output stage of this final FFT stage regardless. So the next part of the question is asking if the sampling frequency used in part 1 was 1200 Hz, what's going to be the amplitudes and frequencies of the two largest spectral components present in the signals. Alright, so in this particular case, we know f of s is equal to 1200 Hz. And because f of s here was equal to 1200 Hz, we need to figure out what's going to be the frequency bin spacing where we know n here was equal to 8. That means delta of f here is going to be f of s divided by n. 1200 divided by 8 means that we will have a bin spacing of 150 Hz for each frequency component. Our biggest component here is the DC component, which has a value of 15. And then the biggest spectral components here are going to be at where we have the biggest real values and the biggest imaginary values on the output stage here. So you can see that the biggest real value here is minus 5.414 and the biggest imaginary value here is 7.243. So the biggest spectral component here are going to be at the pairing of this minus 5.414 minus 7.243 and its complex conjugate here, which is going to be positive that of the imaginary value. So I'm just going to write this out for you guys. So the biggest component here is the DC value, 15, and then the biggest spectral component is at minus 5.414 plus minus G 7.243. And if we take the magnitude of this, this is going to be 9.0428. So that basically answers the second part of our question 8, which is find the amplitudes and frequencies of the two largest spectral components present in the signal. Alright, so are there any particular questions regarding the solution here for question 8? Oh wait, there's one other thing. I forgot I need to put the frequencies here. So this here is at f equals 0 Hz. And the frequency here for the biggest spectral components would be at this is at the first harmonic and this is at the last harmonic. So this will be at 1 f of s and 7 f of s. Means this is at, sorry, 1 f of s, 1 delta f and 7 delta f. This is at 150 Hz, and then this one here would be at, I believe, 10 Hz. Alright, so any particular questions regarding the solution for question 8? How did I get, I mean the delta F? Remember, each one of those components there in the FFT is spaced accordingly depending on the sampling frequency here and number of points that we have. So that's how we calculate it for delta F being equal to the sampling frequency divided by the number of points. So each component here and the FFT is going to be spaced by delta F frequencies. So this here will be at 0 because it's at the DC component. And then each harmonic component will be 1 delta F, 2 delta F, 3 delta F, 4, 5, 6, and 7 delta F accordingly. So the calculation for delta F here is equal to F of S divided by N, which is the sampling frequency divided by the number of points we have for the FFT calculation. Yeah, right. Alright, any further questions? Alright, doesn't seem like we have any further questions at this point. Alright, so I'm leaving the solution here in case we do need to backtrack it at some point, in case of anything. So let's see what the next question was. That was question 9. Sketch the butterfly diagram for the output stage of the 16-point FFT. Oh, okay, so this one is pretty straightforward. I'm going to do the sketch for you guys. See how easy it is actually to sketch this out. I'm just backtracking here a little bit because I need to label my question. There would have been eight. This one here would be A. Alright. So this is just going to be the output stage for a 16-point FFT. So that means we need to have an 8-point DFT here, being that we know it's 16 points, and if we divide that in half, meaning 8 points there is going to have no total factors, but then the next 8 points here will have total factors. So we say this here is also the next half of the 16 points, being the 8-point DFT. And then we don't need to draw out the entire thing. We can just basically illustrate for one section of the butterfly diagram how it is that we go about doing it, or just for 2 sections in particular, how we go about doing the calculations. So you can see here that this here being the first point that will be going towards the output stage of the 16-point FFT will match up to the first point here that does have a total factor. So the first point that doesn't have a total factor will match to the first point that does have a total factor. And we can put the associated -1 here. And the output here is going to be x of 0. And this output here would be x of 8. We also need to put in our cross points to represent our total factor, sorry, our butterfly diagram calculations. We draw in our cross points here to represent this. And then because this calculation just keeps on going, we'll just put some dots there to indicate, okay, these calculations keep on going. But then we're just drawing the last line here for our calculations, just to illustrate the second part of our FFT calculations here. So this here, this output, because this is x0, we have x1 going straight down the line. At this point, this here is going to be x7. And then, because we drew this last line here for the first half without any total factors, that means we're going to have to draw in the last line here to match up with this, so where we do have the total factor matching up. So we're going to put in our total factor here to match, and the output here is going to be x15, because we're going from 0 to 15, representing our 16 values. Just putting our dots here to indicate, okay, this calculation keeps on going. And then finally, we just need to put in our cross points for our calculation for the FFT. So we put our cross point there, and our next cross point here, a cross point here, throw that off. And that's basically the sketch for the 16-point FFT that we need to draw. Because we don't need to draw all the calculations because it's understood that we're going about doing it. The things that we do pay attention to in particular is like how we went about drawing the cross points here for the butterfly diagrams, the placements of the total factors and the minus ones, as well as what's going to be the total factor index that we're going to be using in particular for this calculation. So because the question here in particular asked for let's backtrack here, the output stage of a 16-point FFT, this means this is going to be the final stage of that 16-point FFT. So that's why we have an 8-point here and 8-point here, because this is going to be, write this in, 2 to the 4. This is the 4th decimation stage. And it's 16 values. That means we need to break those 16 values into halves. So that means the first half of that 16 values will not have any total factors, and the second half of that 16 values will have total factors. And because you know it's 16 here, the total factor index is going to go to the W16 as required. So because this goes from W16 and this is going up to basically W16, if I'm just repeating myself, for this half here, which does have total factors, that means it goes from W16 0, 1, 2, 3, 4, all the way up to W16 of 7. And the minus ones here represent the second half of these total factors because of the symmetric property. So we pay attention to if you got the total factor indexes here correct. Indices, sorry, correct. So that needs to be W16 of 0 and then W16 of 7. And we also pay attention to that you had the corresponding minus ones here to match, as well as drawing the cross points correctly for the butterfly diagrams. Finally, we'll be watching that on the output stages here. We know for that first one is going to be x of 0. The next one here for the second part of the butterfly diagram is going to be x of 7. And then we watch for the matching values here, which is going to be x of 8 and x of 15. So for this one here, if we watch this butterfly, that's x of 0, and the matching calculation for this will be x of 8. And then for the last part here, which doesn't have a total factor, that does match the last part that does have a total factor, it's going to be x of 7 and x of 15 accordingly when you're doing the sketch. So we pay attention to these little details, but you don't need to draw all the butterflies associated with this sketch. You just need to show for the first calculation and the last calculation only. Alright, so that basically brings us to the end of question 9. Is there anything that seems a little bit unclear how we went about doing this sketch? Okay, it doesn't seem like we got any questions for question 9, so hopefully that was pretty straightforward. Alright, so that's the end of problem set 2A there, with regards to the questions themselves. And now let's move on to problem set 2B in particular. Alright, so the problem set 2B here. So I did say question 2 is basically just some MATLAB code, so I will basically give you guys some example MATLAB code, how to go about getting sketches here and how to compare them and so forth. But the main points of focus here are going to be question 3 here and question 4 and how we go about doing this in particular. So we're going to be starting with question 3 here in particular. 3. And question 3 here basically asks us to apply an 8-point window of your choice to the sequence given in problem set 2A, question 7, and repeat the question and note if there's any improvement in the results. So for the 8-point window that I'm going to be using here, let's check this back. I'm going to use the Hammond window, and the Hammond window has an equation that is W of n is equal to 0.54 minus 0.46 cosine of 2 pi n divided by n minus 1. And in our case, we know that from problem set 2A question 7, there was 8 points we were dealing with. So n here is equal to 8. And then the common n here will be 0 to that capital N minus 1. So that's going to be 0 to 7. So we can just plug this in straight into Octave. Select here. Let's bring this down here so we can see our equation. Right. Oops. Nice, right. So we know that capital N here is going to be equal to 8, and then common n here is going to be from 0 to 7. And then we can calculate out for our Hammond window here in 0.54 minus 0.46 by cosine 2 by pi by common n divided by capital N minus 1. And we can see here immediately that we were able to calculate out for all the values required for 8-point Hammond window as required from the equation itself. So we're going to come back to that in a little bit, but now we're going to actually I'm going to show you guys how to actually apply this to our original signal from problem set 2A question 7. So I'm going to draw a table here to illustrate this in particular, and let's start drawing this table. So our first column of this table here is going to be x of n. I'm going to list out all my x of n values here from problem set 2A. So 0, 0.944, minus 0.623, minus 0.532, 0.974, minus 0.112, minus 0.901, and 0.707. And now I'm going to list out my window values here that I just now calculated from Octave. I'm going to list out each one of these values here. I'm going to be rounding these up to 3 or 4 decimal places. For my solutions here, I've rounded them up to 4 decimal places because the calculations have not been completed as yet. All right, so the first value that we had for our window function was 0.08, which we can see here, 0.08. The second value here is going to be 0.2531, and this is 95, so I'm going to round this up, so this is going to be 0.2532. Now we're going to 4 decimal places. And then the third value here was 0.64236, so this will be 0.6424. All right. And I just keep on going and repeating that process. So this one here is going to be 0.94. The next one is going to be 0.424. I happen to miss something here. 5. Yes, I happen to miss something here. This value is supposed to repeat. 0.954. Let's just verify that. Yep, that value is there supposed to repeat. 0.644. 0.2532.8. So now that we have our original X of n signal here and the window function vector values that we just calculated using Octave, the next step is to actually calculate for H of n, which is going to be the multiplication of X of n here and W of n. Is X of n by W of n. So we just basically multiply these values straight across each other to get our H of n signal, which is a multiplication of our corrupted X of n signal that was not sampled properly, by the windowing function that's going to attempt to mitigate the aliasing effect because of this incorrect sampling that was done at the incorrect frequency. So we just multiply these values straight across. So the first value here is going to be 0, and this one is going to be 0.239 minus 0.4002 minus 0.5078, 0.926 minus 0.0719. Wait, am I missing another value again? That 3, 4, 6. No, I'm not missing values. I'm just not lining them up properly. Minus 0.81 and 0.05. All right, nice. So we just draw some connecting lines here. Yeah, so I can have these lines here to visually assist me which values were what, matching up to each other. All right, so I'm going to show you guys how to automatically calculate this in Octave as well, because we already have our W vector here. Let's actually just plug in our X vector one time. So we had X here was equal to, I'm just going to backtrack here a little bit to get my X vector, was 0. Wait, hold on. Oops. Let's see. All right, here we go. So 0, 0.944, negative 0.623. And you can note here that for each value, I'm spacing them out accordingly when I'm inputting it into the vector. 0.532, 0.974, minus 0.112, minus 0.901, and 0.707. Right, and then I can say H here is equal to X star W, but this isn't going to work because it's going to be, okay, this doesn't match up to being a matrix multiplication. So in order to get this to work, I need to make sure it's multiplying element by element. So it's going to be H equal to X dot star W. So that way it multiplies the first element with each first element in the next opposite vector. So we go 0 by 0.08, and then 0.944 here by 0.253, and so forth. So this star, this dot star here, means multiply each element by its corresponding element position in the next vector, and so forth. I believe that's also somewhat similar to what the dot product is, but the dot product just basically sums all these values and gives you a final value. So this is just the element by element multiplication for two vectors that are in the same positions and lengths accordingly. So yeah, this basically gives us all the values calculated out first, and we can just verify these values here that we just loaded. So these automatically calculates out are the result of the window function here being multiplied by the original signal. And then because we already have our window signal here, and the question here just basically was asking us to follow the same approach that was used to develop the FFT. No, sorry, wrong question. Repeat the question here and just note any improvement in the result. Well, we don't need to go back and do all that FFT itself. We can just compare it immediately here using Octave. So we have our X sequence here. So let's find FFT of X. And then we have our H sequence here, which was a result of the window function being multiplied by X. And then we can just do FFT H. And then we can just compare the two answers here accordingly to see what's going to be the key difference. And immediately we can see that our DC value here, being the first values that we had, the DC value using the window function here has been mitigated in comparison to when we just had it with respect to just the X signal by itself. And then if we watch each one of the harmonics here, and this is the first harmonic, and then second harmonic, and the third harmonic, you can see here that the window function actually mitigates these as well only. And then when we get down to the center frequency, you can see here that the center frequency has actually been improved in comparison to the original signal that was here for our X signal. So we basically can see the effect of the windowing function here as a result of each one of these that were just done. So the DC signal here was basically mitigated in comparison, and then all the harmonics were also mitigated as well as a result. And the center frequency, which was basically the important point in using this Hammond window, we obtained closer to what the actual true center frequency would have been if this X signal was sampled at the correct Nyquist frequency. Alright, that basically brings us to the end of question 3 here. Are there any particular questions regarding how we went about doing this? We actually don't know what the correct center frequency is going to be if you're asking if we have some sort of reference, because to begin with, the X signal was not sampled at the correct sampling frequency, meaning that it was not correct. It was not at the correct Nyquist frequency. So once you have incorrect sampling as a result, you're going to get the aliasing effect, which we observed a few lectures back. Now, the purpose of windowing is trying to attempt to mitigate these aliasing frequencies components, which are basically unwanted frequency components due to the incorrect sampling. And as a result, because of the shape of the window, so I'm just going to do a quick sketch here for our Hammond window. A Hammond window, basically, if you just sketch this, it looks something like this. And basically, what that means here is that for each part here, you can see the attenuation factor when you watch it regards to the magnitude. Let's say here was a magnitude of 1, there's 0.9 going all the way down to 0. Each one of these magnitudes here, when we multiply it accordingly, using our original signal and the windowing factor, it mitigates those amplitudes as well. So it tries to mitigate those amplitudes as a result. So once we go into the FFT of the actual signal, being the FFT of the signal here being H, those amplitudes have already been mitigated. So once you do the FFT and once you get the frequency result, as a result of that FFT being applied to already mitigated amplitudes, that means for each one of those frequency components, the amplitude is also going to be mitigated. Now you can also note here that because of the shape of this window function here being a Hammond window, the amplitude is max here at the center. And the reason for this being is that we're trying to maintain what's going to be the frequency content information at the center, being the center frequency of our signal. So we try our best to maintain what the amplitude is going to be at the center, as well as mitigating the unwanted frequency components or the unwanted amplitudes that are contributed by these unwanted frequency components. So we don't know what the correct value of the center frequency is going to be because, like I said, the X signal here was incorrectly sampled to begin with, but we try to approximate and guess to what it can be as close as possible to what its actual value can be. So that's the purpose of using the windowing function to try and mitigate the amplitudes of the side frequencies, as well as to maintain the central frequency component as close to as possible what it should have been. Right. Any further questions? Okay, it doesn't seem like we have any further questions regarding this in particular. So let's go on to the next question, which was question 4 in problem set 2b. Three, four. So question 4 here basically asks us to do the inverse FFT of the 8-point spectrum from the result obtained from question 7 and problem set 2a. Right. So that means instead of us going from the original signal to the FFT representation, we're just going to be doing the reverse in particular to get back to our original discrete time signal. And in order to do this, that means we're going to have to sketch out each one of the butterfly diagrams in turn, but instead of going from first to third decimation stage, we're going from third back to the first decimation stage. And then will finally do the bit reversal process to get back to our original discrete time signal as required. So we're going to do this step by step in order to observe how we go about doing this in particular. So we're doing the inverse FFT, IFFT. That means we need to start at third decimation stage. And I'm going to use placeholders for each one of these in particular. So you can say Z1, Z2, Z3, Z4, then Z5, Z7, 8. And we need to draw butterfly diagrams, match back to what the calculations will actually look like. So we know this being the third decimation stage, this is 2 to the 3, which is 8 values. So we need to group half of that with the next half. So the first half of this is going to be without any total factors, but then the second half will have total factors. And it's being the third decimation stage because it's to the 3, 8 values, meaning that our 12 factors here will be at W of 8. So for this first one here, this is going to be W8 of 0. This one here will be W8 of 1. This one will be W8 of 2. This one here will be W8 of 3. And for each one of these total factors, we need to have an associated -1 because of the symmetric property. And then we need to draw our butterfly cross points. So for the first value here that doesn't have a total factor, it needs to match with the first value that does have a total factor. Cross points here only, and so forth. But I'm going to go in turn as we keep on doing this. So the output of the FFT here, which we had from problem set 2a, I'm going to be writing it out here. 8 J into 6, 2.8 J 0.7 minus 2.8 plus J into 0.74 minus 1.7 8 minus J 0.4 2.48 plus J into 0.7 and then 0.688 plus J. Right. So for first butterfly diagram here, which we are calculating for, because we need to figure out what's going to be Z1 and Z5, we're going to actually write up the equation here about how we obtain to each one of these output values. So in this case, this was Z1 here, plus Z5 by W8 of naught equals to 0.457. And then conversely, Z1 here plus Z5 by W8 naught by -1 is equal to minus 1.557. So Z1 here plus Z5 W8 of naught minus 1 equal to minus 1.7. And we see here basically we have a simultaneous equation here to solve in particular. So I'm just going to extrapolate these out to make them a little more simple. So this is going to be Z1 plus Z5 equal to 0.457, and then Z1 minus Z5 equal to minus 1. And then I can just say for this equation here, I can say Z1 here is equal to minus 1.557 plus Z5, and I can substitute this in accordingly. So our first equation, so let's call this 1 here, 2, substitute into 1, so I get minus 1.557 plus Z5 plus Z5, 0.457, and I'll get 2Z5 here is equal to calculator for this calculator here, 0.457 add 1.557 equal to 2.4. So I can say Z5 here, here equal to 1.007. And because I've calculated for Z5 here, I can just solve for Z1 now. So means that Z1 plus 1.007 equal to 0.457, Z1 here is equal to minus 0.55. That will be solving for Z1 and Z5 here accordingly when we're doing our reverse FFT here for a third decimation stage. So we have Z1 and Z5, and then we just repeat the process as we keep on going on. So for the second value here that doesn't have a total factor associated with it, we need to match this with the second value that does have a total factor. So we draw in our cross points here. And then we watch the calculations for these in particular as well, and we just basically repeat the process as we keep on going. So in this case, this is going to be Z2 plus Z6 W8 of 1 is equal to this complex value here, 0.6488 minus J 0.1486. And then we have Z2 here going down here, plus Z6 W8 of 1 by -1 is equal to minus 2.5968 minus J 0.4074. So we basically just keep on doing a series of simultaneous equations to go ahead and solve in particular. So in this case, this is going to be Z2 plus W8 of 1 6 equal 0.688 minus J 0.146 and Z2 minus W8 of 1 because of that negative 1 that we had. Z6 equal to minus 2.5968 minus J into 0.40. And because this is basically a series of simultaneous equations, you can just go ahead and be like, okay, let's go about subtracting the two. So subtract equation. So Z2 minus Z2 here, let's give you 0. W8 of 1 Z6 minus W8 of Z6 means that's going to be 2 W8 of 1 Z6. And then we just need to do the subtraction of these complex values here. So let's just watch this here for the real part. 0.6488 add 2.5968 equal to 3.2456. And then we have, for the imaginary part, we have minus 0.41486 minus, so that becomes positive 0.4074. So we're just going to be, right, so minus 0.1486 plus 0.4074 means we have plus J 2.588. And then we can just basically solve for Z6 here if we use an octave. So I'm just going to bring back octave here in particular, like this. So we have a W8 of 1 factor here, which we can calculate for. I'm just going to calculate for this only. So this W8 of 1 here is going to be exponent of minus J by 2 by pi by 1 divided by 8. And then we can say that 6 here is equal to 3.2456 plus J by 2.588 divided by 2 by W. And we get Z6 here equal to this value, which I'm going to verify with my answers here. Okay, I may have done something wrong here. I'm just verifying my answers and it doesn't seem to be correct. So let's backtrack a little bit to see what did I do wrong. So maybe when I was doing the subtraction here, I did something wrong in particular. See if I did something. So extrapolate this. X. Put that in there. So 2W and then X value. Adds to. Let's check this back. Alright, so I'm just checking my mathematics here to make sure I did everything correct. Let's see if I did everything correct here. This correct. Right. I would have 0.6488 minus j by 1.6. Then I need to add 2.58, add j 3.2456 plus that's what I did wrong. My imaginary value here is incorrect as a result. Yeah, because I did my calculations here wrong. Okay, so this imaginary value here is wrong. Right, so Octave actually calculated it correctly for me. So this here is going to minus 1.0786. 0.0786. Right, nice. I'm still watching this and I'm thinking something else is, this doesn't seem to match up. So I'm just going back in my Octave calculations just to see what did I do. .1486, that's why I did wrong. Right. There we go, that's the correct answer. So this is going to be 0.2588i. Right, so that actually is the correct answer that we're working towards. And now that we actually do have that, so let's say this here, I'm going to store this as t. Let's say temp is equal to the answer here. And then we're going to say z6 here is equal to temp divided by 2 by w. That should be the correct answer. Yes, that is the correct answer. So our correct answer here is 1.056 plus j into 1.239. Right. So that's one thing to note here. Yeah, the subtracted value, j values are incorrect. Just be a little bit careful when you're doing the mathematics here, because as you can see, I made a mistake when I was doing the subtracted j values. So this we can obtain our z6 value here. So that means we can just plug that back in for z2. The z2 here, as a result, once we plug it back in, see what I had for my z2 value is going to be minus 0.974 minus j into 0.278. And let's verify this, because we have our z6 here. So we can now solve for z2. So we're just going to go back in Octave here. And we can say z2 here equal to back 0.6488 minus j by 0.1486 minus w by z6. My math here is a little wrong. 0.974. Right, yeah, that's correct. Nice. Right. So basically this process keeps on repeating itself throughout the entire diagram itself. So if we go back here to our diagram and let's say, okay, let's solve for Z3 and Z7. See here that Z3, the cross point goes here. Z7, the cross point goes here. And we're matching back our butterfly diagrams. So we can write out the equation for Z3. It's going to be Z3 plus Z7W8 of 2 equal to this value here. Write that out. Z3 plus W8 of 2 Z7 will be equal to 2.48 minus J into 657. Okay. Give me 1 second, guys. I need to be right back. I have to handle one thing. So take a quick 5-minute break. I'll come back in a little bit. Alright, I'm back at this point, so let's just continue the working that was required. Right, so Z3 plus Z7 WH of 2 equal to that complex value there. And then simultaneously Z3 minus W8 of 2 Z7 will be equal to 2.48 plus J into 657. So then we can do the same thing as before, where we just subtract equations. So we get 2 W8 of 2 Z7 equal to 2.498 will cancel, and this here will just become twice that of the J value. But it's going to be minus, so it's going to be minus J here of 0.657 by 2. Let's just put this in. Minus 0.6 negative 1.314. Correct. So then we can calculate out for Z7 here. And let's use Octave here to help us out a little bit. So we want to be calculating for W here. With exponent of minus J by 2 pi by, this is W8 of 2, so this is 2 divided by 8. Get our W value here. And then, right, that's fine, because it's just an approximation for. We're fine with a little bit of it's fine. And then our calculation here was this. So that 7 here was equal to minus J by 1.4 divided by 2 by W. See if that matches up to what I had, because I have a feeling my. Right, okay, so that matches up to what I did have here. So Octave does some weird rounding offs at some case in particular. But once you see, like, if it's like e to the minus 17i or something like that, this value is basically 0. So you can just ignore that value here. This 6.5700 by e to the negative 0.1, this e here basically means 10 to the power negative 1 as required. So this here, if it's going to be 10 to the negative 1, this here is going to be 0.657. Just pay attention to that when you use an Octave in particular. Once you see like these weird exponent values, it's just basically, as a result, these values here are really, really small in nature if they have some kind of weird value in particular. So like if you see e to the positive 0.0i, this just is going to be 10 to the power 0. And then if you see e to the negative 17, this is like 10 to the power negative 17. So as a result, this value here is going to be really, really small. So that entire value here will just approximate to 0. And when I did the calculations here, you can see here that for the imaginary value, this is e to the negative 17, meaning that's 10 to the power negative 17. So this value here, you can just approximate straight down to 0. This value here was e to the minus 0.1. So this here is just 10 to the power negative 1. And if we multiply that by 6.57 here, we get 0.657 accordingly. Just pay attention to the round off factors here when you use an Octave. I think MATLAB will actually give you a more accurate answer as required. So now that we have Z7, we can solve for Z3. And Z3 there was basically going to be 2.49. And then in the interest of time, I'm just going to put what the answer for Z4 here is. Z4 will work out to 0.974 plus G 0.278, and then Z8 here work out to be 0.06 minus J into 39. So now we have all our values here for Z1 to Z8, and we're now going to have to set up for the second decimation stage. So the one thing about the inverse FFT is that it is a very long problem. So set up for second decimation stage. So we could say, since we're operating in reverse, yeah, we're going to call our values that we want to solve here y. y1, y0, y1, 2, 3. The indices don't really matter how you label them. I just chose to label them from 0 here on out. So this being the second decimation stage, this is 2 to 2 means every 4 values you're going to have to be dealing with. And then because it's every 4 values you're dealing with, that means that each of these 4 values, 2 of these values will not have total factors, but then these 2 values here will have total factors. So as a result, if we draw our lines here across accordingly, these first 2 values here in this grouping of 4 will have no total factors. The next 2 values here will have total factors, which will go from W4, because of 2 to the 2 means 4. So this here is going to be W4 of 0. This one here is going to be W4 of 1. And then you need to have your corresponding -1s here as of such. And then the same thing happens for the next 4 values. So the first 2 values here will have no total factors, then this one here will have a total factor. That's W4 of 0, and then 4 of 1, and so forth. So the output of the second decimation stage here is going to be the values that we just calculated for Z1 to Z8. So this here is just basically going to be Z1, Z2, Z3, Z4, all the way down to Z8. And just for my ease, instead of just putting these Z's here, I'm just going to put what each one of these are here immediately. I'm just going to rub these off here, because you've seen the illustration for what the outputs are going to be here. So those Z1 to Z8 values we just now calculated are going to be the output of the second decimation stage. So this one here is going to be 0.55. This one is minus 0.974 minus J into 0.278. This was 2.498. This is minus 0.974 plus J into 0.28, 1.007, 0.056 plus J into 1.39, 0.657, and then 1.056 minus J into 1.239. So when we're drawing the butterflies for the second decimation stage, because we're grouping by 4 values, that means the first value here in the group of 4 that doesn't have a total factor needs to match the first value that does have a total factor. So we draw our cross points here accordingly. And then we go about solving for y0 and y2 because of the pair that we see here for our butterfly diagram. So if we watch here, y0 plus y2, W4 of 0, will equal to negative 0.55. y0 plus w4 of naught of y2 is equal to negative 0.55, and then we have y0 minus w4 of naught 2 going to be equal to 2.498, which you can see here, y0 plus w2 w4 naught by negative 1 going to be 2.498, so that is going to be y0 minus w2 w4 of naught y2 equals to 2.498. And then we can just repeat the same instance as before, where we just subtract the both of them. So we got 2 w4 naught y2 here is equal to octave here, and this is going to be negative 0.55 minus 2.498. So we get negative 3.498. So we get y2 here being equal minus 1.524, because w4 of naught is just going to be 1 from our total factor equation. And then similarly, we can solve for y0. So y0 is going to be 0.974. And then we just basically repeat the process as well when we're solving for y1 and y3 here. So remember, y1 here in the grouping of 4 values for the second estimation stage, this is the second value that doesn't have a total factor and needs to map with the second value that does have a total factor. So we draw cross points here. And we just follow the trail of the cross points here to get to our answers accordingly. So this one here is going to be y1 plus y3 w4 of 1 equal to negative 0.974 minus j 0.278. So write that in. This one here is going to be y1 plus w4 of 1 3 equal to minus 0.974 minus g into 8. And y1 conversely minus w4 of 1 3 is going to be equal to minus 0.974 plus j into 0.28. And then subtract the 2. So in doing so, we get 2 w4 of 1 3 is equal to these two terms here will cancel. These two terms here will add, so this is minus that. So we get minus j, let's bring up octave, 0.278 by 2. 0.556. And we can solve for y3 here. So let's bring back up octave here to help us solve it for this. So we're going to be solving for w first. So this is exponent into minus j by 2 by pi by 1 because it's w4 of 1, and divide by 4 because we're at the second decimation stage. So we get our w value here, and then we solve for y3 here is equal to minus j by 0.556 divided by 2 by w. And as a result, y3 here should be, we see the imaginary value here because e to the minus 17, that's a really small value, so that's just going to be 0. And here we have e to the negative 0.1, so that's going to be 2.78 by 10 to the negative 1, so that's going to be 0.278. So y3 here is 0.278. And we can substitute that back in and we can solve for y1. So y1 here is minus 0.974. And we can just keep on repeating the processes as required. So I forgot to put in my negative ones here for my total factors. So for the next 4 values, we just repeat the process for the total factors. The first value here matches with the first value with the total factor. So draw cross points here. And then similarly, the second value that doesn't have a total factor will match with the second value that does have a total factor. Just draw cross points here as well. And we can go about solving them the same way how we went about solving for y0 to y3. So I'm just going to write down what the values are in the interest of time. So we have y4 here is equal to 0.832. y6 equal to 0.175. y5 is going to be equal to 1.056. And then y7 here equal to negative 1.39. So now that we have all those values there for the second decimation stage, we just set up for the first decimation stage. So this is going to be 2 to the 1, which is 2 values. And this decimation stage is just going to be very easy. So let's just call the inputs for these being x0, x1, x2, x3, x4, 5, x7. And then because it's just every 2 values that's going to have an associated total factor, that's going to be W2 of 0 and W2 of 1, which is just going to be 1 and negative 1. So we just put the minus 1s accordingly for each one. So the first value here will not have a total factor or a negative 1. But this one here will have a total factor and a minus 1. And because the total factors here just basically oscillate between 1 and negative 1, we just ignore the total factors and we just put the minus 1s accordingly. So for the next 2 values here, that's going to be there, no minus 1. This one will have a minus 1 here. And we just keep on repeating as we keep on going. There, minus 1. We keep on going. Right. And then the output of this first decimation stage is going to be y0 to y7. So this one is going to be y0, y1, y2, y3 going down the line. But for ease of convenience, I'm just going to put what the values are here. So this here was 0, 4, minus 0.974, 4, 0.28, 0.832, 0.06, 0.175, and minus 1.239. Right. And then, because this is the first decimation stage, and we're just grouping by 2 values, that means this first value here in the group of 2 just matches to the next value here that has the negative 1. We just put our cross points accordingly. And then we can just solve for each one as we keep on going. So if I do for our first one here, this one is just going to be x0 plus x1 is equal to 0.974, and x0 here minus x1 because of this negative 1 equals to negative 0.974. So I can have x0 here plus x1 is equal to 0.974. x0 here minus x1 is minus 4. And then we can just do the same thing as before. Subtract equations. So we get 2x1 here equal to 0.974 by 2. .974 by 2 is 1.948. But we already had a 2 there, so this is just going to be 0.974. And similarly, if we solve for x0, x0 here is just going to be 0. And we just keep on repeating the process as we keep on going. So in the interest of time, I'm going to just write out what each one of these values are. So x0 here is 0, x1 here is 0.974, x2 here is going to be minus 0.63, x3 here is going to be minus 0.901, x4 here is going to be 0.944, x5 here is negative 0.12, x6 here is going to be minus 0.532, x7 here is going to be 0.77. So we have our x0, the x7 values here, but this isn't the end of our process for the inverse FFT. The last thing we need to do is what we refer to as the bit reversal process. So these here being from x0 to x7, we need to get the binary representation of their positions. So this here being at x0 being 0 being the position, this here is going to be 0, 0. This one will be 0, 1. This one here is 0, 1, 0. This one here is 0, 1. This one here is 1, 0, 0, 0, 1, 1, 1, 0, and then 1, 1, 1. And because it's a bit reversal process, that means we need to swap the first and last bits accordingly for each one of these. So, and doing the swap, this here is going to be 0, 0, 0. This one here is 1, 0, 0. This one here is 0, 1, 0. This 1, 1, 0. 0, 0, 1, 1, 0, 1, 1, 1. So these here will indicate what the positions of each one of these x values are going to be after the bit reversal process for the actual sequence for our original x vector to conclude the inverse FFT. So this means here, if we realign this back into positions, so this is bit reverse. So this here is going to be position 0. This one here is 1, 0, 0, so that's position 4. Position 2. This here is position 5. This is position 1. This here is position... Oh, sorry, this one's a position 5. This is position 6. This is position 5. This here is position 3. And this here is position 7. So, zoom out a little bit. So, our actual x vector here, after we do our bit reversal process, we're just going to map back to our new positions as required. So, this one here is at position 0, so that means the value here is going to be 0. Then we look for 1 here, so that's going to be 0.944. 0.944. We look for 2, which is negative 0.623. We then look for 3 here, which is negative 0.532. We look for position 4, which is 0.974. Just breaking this into a separate line. Position 5, which is negative 0.112. Position 6, which is negative 0.901. And position 7, which is 0.707. And that brings us to the end of the inverse FFT process. So it's a very tedious process, but it's simple calculations that you keep on going, which we saw here throughout the entire walkthrough. And it's just basically a set of repeated calculations. You can use Octave or MATLAB to assist you with repeated calculations and so forth. All right, so are there any particular questions regarding the inverse FFT problem here? All right, doesn't seem like we have any particular questions regarding the inverse FFT here. All right. So these sort of problems that we did here in today's session are the sort of problems that you may expect, in particular what may come on the midterm, or a type of problem that may come on your final exam as well. So it's important to just review material and see how you went about attempting this problem. And it's also quite important to attempt this problem on your own and just use the video here as a reference to see if you're on the right track and so forth. So before we end today's session, I do have a little bit of important information regarding what's going to be going on with the midterm next week, Wednesday. So in particular, your midterm is going to be on Wednesday, 3rd of March, from 8 a.m. to 8 p.m. meaning it is a 12-hour window. Your midterm will be open book. Well, obviously. Your midterm will be marked out of 80, so 80 marks, and there will be 2 questions on the midterm, which are going to be uneven weightings. Any material up to the end of the first 8 lectures, I'm repeating that, up to the end of the first 8 lectures will be tested on the midterm. The submission period for that midterm would be from 9 a.m. to 8 p.m. of the same day. And submitting your files online via My Learning, PDF files will only be accepted on the submission portal. And the maximum file size for this PDF will be 20 megabytes. Students will be allowed to use OneNote or any other compatible software if they wish to use an electronic stylus to write their solutions on their device instead of writing the solutions on paper with ink and taking photographs. In doing so, for all submissions, only handwritten solutions will be allowed. Any typewritten content will be automatically disregarded for marking. Please pay particular attention to that. All your solutions need to be handwritten. Anything that is typewritten will be disregarded for marking. It is highly suggested to use an app or PDF printer software on your computer in order to create the PDF consisting of the clear, high-quality resolution captures or photographs if you do end up writing your solutions on paper with ink. Please also make sure that your photographs are in focus and as clear as possible, and make sure that your photos are captured with proper lighting and no occluding shadows. Before you do form your PDF, verify the quality of the photographs on your laptop or computer. Unclear and out of photograph photos unclear and or out of focus photographs can and most possibly will be disregarded for marking. If for some instance your PDF file exceeds 20 megabytes, try reducing the resolution of each of your photographs until you achieve the required file size. Most importantly, for students who do not have access to My Learning, meaning that you got suspended for some weird reason because of administration and so forth, or your registration is still pending and whatnot, please email me immediately so that I can make arrangements for you to send the exam to you via email, and as well as to accept your submission via email. Only these students who have emailed me will be given this opportunity to receive your exam via email and to send your submission via email. If you do not email me, that means your submission is going to be coming through my e-learning. So all other students who have not made this arrangement with me, who have not made this arrangement with me up front, must submit their submissions via the designated submission portal on my e-learning. Any other forms of submission, if I have not been informed beforehand, will not be accepted. Alright, so these instructions I just now read out for you guys will also be on a forum post on the course page for my learning as well, for you guys to also review and so forth. And next week Monday there will be no class because of your midterm preparation, so use your time wisely to prepare for your midterm on next week Wednesday. Alright, so just remember that next week Monday there's no class, but from next week Wednesday is your midterm. Typically they will tell you add a plagiarism form to your document, so I suppose you will need, yes, you will need to actually have a signed plagiarism form to your document. So I will add that into the requirement listing that I'm going to post on the forum in a little bit. Alright, any further questions before we conclude today's session? Alright, doesn't seem like we have any further questions. So if there are any further questions after the session has been concluded, feel free to leave them down in the comments below, or you can directly email me accordingly and so forth. If there are any questions regarding the problem sets or any particular questions regarding if you made an attempt on a problem and you need some assistance in case you don't know if you did correct or not, also feel free to email me directly with your attempts before the day of the midterm, so I can actually watch your attempts and whatnot and so forth. Alright, so good luck on your midterm next week Wednesday, and until then, take care, be safe, and I will see you guys soon. Later.